You're sitting in physics class one day and the topic of quantum entanglement comes up. Your head can't wrap around that idea, so you go home to search it up, but it just looks like gibberish. So let me break it down for you. Imagine there are two closed boxes in front of you. Inside each box is either a red or blue marble. From what we know, before opening the box, the marble has a definite color. However, we don't know which color. But in the quantum world, before you look, the marble isn't red or blue. Rather, it's in a superposition, meaning it's both red and blue at the same time. Only after opening the box, the marble is set to a color. Now let's say we link the two marbles so their colors are connected. When you open one box and see a blue marble, you instantly know the other must be red. This is because they share a single joint wave function, a mathematical description of both marbles. Think of a wave function like a manual that holds all the possible outcomes. The marbles share the same one. That means they're just two parts of a single description. So if you learn something about one marble, you instantly know about the other because they follow the same set of instructions. Now let's do this in the quantum world. Let's take two electrons for example. When two electrons interact, their spins can become entangled. If you measure one electron's spin as up, the other will always be down. This happens no matter how far apart they are. Einstein called this spooky action at a distance because it looked like information was traveling faster than the speed of light. However, they are just revealing outcomes that is part of their shared description. Einstein thought that particles had hidden variables that predetermined their outcomes. However, this is where physicist John Bell challenged that. Bell devised the Bell's theorem that showed if particles had hidden instructions, their spin would be different at least 5 out of 9 times. But experiments in 1972 proved that they were only different half the time, ruling out hidden variables and confirming entanglement is real. This could be utilized in the future to create a more secure communication. And there you go. That's quantum entanglement. Pretty simple, right?